So the third day. Now the reason I took it so slow is because if I just went right to this the first day, it would have been way too overwhelming. What we're going to do today is take what you did yesterday, which was find that standard deviation for the sample means. And that's when you divided basically by the square root of n, right? And we're going to use that to go and find some probabilities. We're going to be able to use that to find z-scores. Okay? This one in the red at the top, you've already done that. That's what we've done for z-scores when we started it. This is to calculate the probability for individual members. That's the key. Individual members of the population with a normally distributed random variable, blah, 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 blah. Now, what if it's not normally distributed? Well, that's what you've been working on. You make it normally distributed, okay? But if this one is, and so z equals whatever x value you want to know about minus the mean divided by the standard deviation. That's if all you're concerned about is an individual member. You did that a long time ago. This one here is if you want to calculate the probability for basically the mean of some sample. Okay, so this is a sampling distribution of sample means. That's what we're talking about. And you notice you pretty much do the same thing. You take whatever x value you want, but that x value now is going to actually be a mean. And you're going to subtract the actual mean of that sampling distribution. But here you have to find that, which is what you found yesterday, which is right there, right? That's what you did. My suggestion to you is don't try and memorize that formula. Remember how to do this and just put that number down in for the standard deviation. It's the best way to do it, and that's why we took it in 3 days. You know how to do that part. Let's get that number and just put it in the standard deviation location. Okay, it's easier to think of it that way, I believe. So let's take a look at our first example here and see if we can make some sense of all of this. The table at the right displays the lengths of time that they spend reading the newspaper by age. Probably not too surprising, right? That's believable, right? So that's the average minutes. So do you agree all of these over here are means, right? And here is it's been divided up. Okay, so 65 and up, I would believe that they spend a little bit more time. 18 to 24, probably not all that much. So do you believe, if you look at this, if I made a distribution of this, is this normally distributed? No, it's not, is it? It keeps going up, right? So that's not normally distributed. So what we're going to have to do is we're going to have to work on that. So you randomly select 50 adults, age 18 to 24. So we are most concerned about that, correct? Okay, so we're going to stop. We're just going to worry about that. And so what's the probability that the mean time they spend reading the newspaper is between 8.7 and 9.5 minutes? It's saying assume that the standard deviation is 1.5 minutes. So they took some sample of those age 18 to 24. The standard deviation was 1.5. And what's the average? 9. It says it in the table. The average minutes, 9. So we know, and here's how I would look at it. We know the mean is 9 for this, correct? We know the standard deviation is 1.5. Do we really know the distribution of the data, though, just for the 18 to 24-year-olds? Did they give me that information? No, what did they give me? They gave me the mean, and that was it. But they said they went in there and they picked 50 of them. Do I know which 50? Nope, it better be also random, right? Remember, if you take that word out, all this just goes away. So we don't know, so we better make sure, it's 50, right? So can we use the central limit theorem? So we can change this to a normal distribution even though we have no clue what the distribution looked like in the first place. We have no clue whatsoever. All we know is the mean. And we took a sample of 50. So we know that. We know the mean of the sample means. Because we chose at least 50. We know what that mean's going to be. I haven't seen a single of those 50 people. I don't know any of those answers, but I do know what the mean's going to be. It's amazing. It's going to be 9. And I can even find the standard deviation of that. That's what you did for today on almost every single problem, right? You basically took the standard deviation and divided by what? Square root of n, right? So what does that mean for this problem? Again, am I seeing any of this data? I'm not seeing anything. All I know is the mean is 9, and there's 50 of them. So we know the standard deviation is right here. It's 1.5, right here, over the square root of 50. I don't think this was the nicest number in the world. So we'll kind of approximate. I got 0.212, so yes, whoever said 0.21, that is correct. And so that we know is this. And if you want to write it over here, some people like to that. Okay. Well, we found out a lot of information about this, haven't we? We're doing awesome. But now what? We have to first decide, well, which one of these two do we fit better into right now? Yeah, we're doing more the bottom one, right? Because we're trying to find some mean of some sample size, right? Am I looking for just one particular individual member? No, I've got 50 of these things. So I'm not looking for that top one. I'm looking for this bottom one. So we know the formula we're going to use is our z-score. So now we've kind of made it a normal distribution, right? Is it necessarily the standard normal distribution yet? No, that's what the z-score is going to do. You see how we're working towards that standard? Okay, so we know we're going to take x bar minus mu of x bar over standard deviation of x bar. Do I know all of those bits of information? Yeah, I do. In fact, I have 2 of those x bars. Here's one of them. There's the other one. And it has to be in between, so we're going to find both of them. We're going to go find them in that table. We're going to find their probabilities. And if it has to be between, we're going to take the farthest one and subtract that smaller one. Okay? Because what we're really asking at this point is, we're saying we've gotten to something like that. Do we know it's the standard normal distribution? No, but we know the mean. What's the mean? It's 9. And I'm looking to find from 8.7 to 9.5, correct? When you get a z-score and go to the standard, if I do 9.5, I find everything to the left of that, right? Everything. And then when you do 8.7, you find everything to the left of that. So if you want just between, take all of this for 9.5 and subtract what you get for 8.7. Okay. But we got to get the z-score again. So let's call it z-score number 1. Use the formula. Yes. Oh, you already have it? Oh, I'm behind. Okay, I'll catch up. So this is the mean I want to know about, and that's a mean of 8.7, right? So it's 8.7 is the mean I want to know about, minus the actual mean, which is 9, divided by the standard deviation of those sample means. Well, we just calculated that. What is it? It's 0.212. You see what I mean? If you kind of do the formula in a couple pieces, it's a little bit easier than trying to do it all at once. I think it's just too complicated. So what z-score are we looking at? Negative 1.42-ish, right? Now, does that make sense that this one over here is a negative z-score? Yes, because it's to the left of the mean. Okay, so that makes sense. Let's go get our z-score number 2. So we'll say this is z-score number 1 right there. Z-score number 2 will be that one. So z-score number 2. Well, now the mean I'm looking at is that. So 9.5 minus 9 divided by the standard deviation, right? Whatever that is, which is 0.212. And our z-score for the second one, ooh, it's out there a ways, huh? So do we agree with 2.35? Yeah? Does that make sense that that one's positive? Because it's to the right. And actually quite a ways, isn't it? Okay. So do we have those two scores down? We do. So now you have to go to your table, find negative 1.42 and 2.35. I can't remember how good your tables were. Were they pretty good? I think they were, weren't they?
Yeah, they go.
They go up pretty good, don't they? They go up to the hundreds? Good. So I'm going to, is it okay if I erase some of this stuff? Because my tables are in there. I just have to get this out of the way. Everybody got a z-score of negative 1.42? Maybe I'll put it underneath. Negative 1.4, wow. 1.42 is the z-score for that one, and 2.35 is the z-score for that one, right? All right. So in your table, you go to negative 1.4, and then you go over to 2. And so negative 1.42 is right there, right? So this number, so they're saying this stuff right there is 0.07780. Or in other words, 7.8%, so not much, right? They're saying this one, so 2.35. So 2.35. We're saying that one is 0.99061. And that's all of this. So in other words, I want to be able to go in there. Whoop. Uh-oh, now I've done it. No, now we're in trouble. All right. Yeah, we actually might be in trouble now. We're going to go subtract that out, right? So what are you going to do? Well, take 0.99061 and subtract 0.07780, and you will have the probability. Point. Well, it's definitely 0.9 something. 1.281, something like that. So do you think 91.3% chance? Now the hardest part for people to understand is we're saying that the mean falls between 8.7 and 9.5. So you went out there and you got 50 adults 18 to 24 that were that age, and you got all that information, and then you took the mean. Okay, and then maybe somebody else did it again. Somebody else did it again. The chance of you coming with something that's below 8.7 or above 9.5 is not very good, because you're going to be between those two 91% of the time. Your mean will be between those two very, very frequently. And that's what this is saying. Does that make sense? Okay. I hope it does. Makes sense to me. Okay. So what we're doing is we're taking information and we're finding something about the sample means without really seeing a whole lot of data. Let's try another. The mean rent of an apartment in a professionally managed apartment building is $780. Oof. You randomly select 9 professionally managed apartments. Ooh, 9 seems to be a slight problem. What is the probability that the mean rent is less than $825? Assume that the rents are normally distributed. Oh, so we can do this one. Otherwise, 9 would have been a problem, right? With a standard deviation of 150. Well, let's start filling in the things we know. The mean is 780, right? And so then we should know that. But the only reason we know that is because of, yeah, it was normally distributed. And so that's just horrible. So this is the mean of the sample means. And so that's the same thing. What's the standard deviation? I'm trying to kind of keep them sorted here. 150. So let's go ahead and this is how I would suggest. Let's just go find that and have that information down instead of trying to do it all in one piece. So we know that I have to take 150, what it was, and divide by square root of 9, which in other words is 3, right? So 150 divided by 3 is 50, right? Sometimes I cheat a little bit with the numbers. It's okay. So now we found out what it would be if it was normally distributed, but we don't know the standard normal distribution. So again, of the two, I'm not doing an individual, I'm doing the means again, right? So we're going to do right? Yeah, that's a minus. What's the equal sign doing there? Now, what X bar are we concerned with? What mean am I concerned with? That the mean rent is less than 825. So for me, X bar is 825. So Z equals 825 minus the mean, which is 780, right? Divided by that standard deviation we just found, which is 50. So what Z score am I most concerned about? 0.9. Okay. What's that? No. It adds it up for you. Yeah, the standard number distribution does it for you. Yep. That's the beauty of it. All right, so Z being 0.9, so it'd be 0.9 and then the zeros, right? So now the mean rent is less than that. So is that the answer, or is this where you do the 1 minus thing? Yeah, that's the answer. So it's 0.81594, right? Or 81.6% of the time. What would I change to this problem to make it that I would have to do the 1 minus? Yeah, more than 825, right? Because what you're doing, again, always think back, well, that's terrible. But anyway, always think back to this graph. We know what's right in the middle. What's right in the middle? 780. And 825 is somewhere over there, right? I want to know what's the probability. So in other words, what's that? Right? So did it make sense that our z-score was positive? Yeah, it's right in the mean. So it does make sense.
So when you do 1 minus 1, it's
Well, no. When you're doing the 1 minus thing, you're figuring out that. Right there. What's left over.
so you just take that number minus that
1 minus this number would give you that number out there. Yep. Well, that's not so bad. Credit card balances are normally distributed. Well, that's a good thing, huh? Where did this thing go? I really freaked it out, didn't I? Oh, well, we'll have to find out if we can get that back. With a mean $2,870. That's a pretty good balance. And a standard deviation of $900. So that means it's not even a high, it's a high balance, but it's also fairly spread out, right? There's people that are well above that, right? And there's some people well below that. That's kind of what it means. It's very spread out. That's what the standard deviation tells you. So what is the probability that a randomly selected credit card holder has a credit card balance less than 2,500? Okay, random is a keyword. There are also, this one has a few other keywords. Or it's actually missing a word. I'm not asking about the mean.
so 1.
Yeah, and but I'm not asking you about the mean, though. I'm asking about a card holder, individual member of the population. I'm not asking about the means anymore. So if I'm not asking about the means, you just get to use that. And if it's already normally distributed, there's not a whole lot much to worry about. Just get the z-score and we're done. Or, well, once we find out its area. There is no need to find the means because it's not in this problem. Okay, and we're going to do, the next one will be with the means, then we're going to talk about the difference. Okay, it's pretty important, I think. So what particular x value am I concerned about? 2,500, right? Minus the mean, which is 2870. Now, this is below the mean, right? You agree? So this z-score is going to be negative. Now, what do you divide by? 900. Very good. Because I'm not asking about the sample means. I'm just flat out saying, tell me about this one score. Less than that. Okay. So, what is it? Negative. Negative 0.41. Well, now what? That's my what? My z-score. Because again, we're looking at this. We know the mean is 2,870, and we're over here at 2,500, and I want to know this. You should. Negative 0.41. Negative 0.41, right? So it's 0.34090, or in other words, 34.09%, right? That's believable, I suppose, especially if the standard deviation is 900, right? Because 900 gets us way over, down into there, right? So, and our z-score of negative 0.41, then that makes sense. I'm actually much closer to this mean than I made it look here in my picture, right? You basically found that. And so that, I believe that to be true. We're going to wait to talk about what that means until we do the next problem, and then we'll talk about them together. Okay? So this one we select 25 credit card holders. what's the probability that their mean credit card balance is less than 2,500? Now, before you start calculating this, do you think that this probability will be higher or lower than the 34%? But I'm saying, what's the probability that they're mean? The mean of all those that I find out is higher. Central limit theorem, squeezing it in, all right? When you do the means, it's the central limit theorem. And seeing we are talking about means, we better make sure we can do this. Was the original normally distributed? Yeah, because this is not big enough, right? So, but it was, so we're good. So now we're actually going to use that one. Okay? Because now we're talking about means, and so we have to relate means to means. And so the sample mean I'm concerned about is now 2,500 minus what is mu of x bar? It's the same thing, right? So 2,870, right? How about this one? We take the 900, right, that it was before, and divide by the square root of 25. Because that's your formula, right? Divide by the square root of n. And so in other words, divide by 5. Again, I'm kind of normally nice with the numbers when I'm up here. Your assignment doesn't work out so nice, but you have calculators, so it's okay. And what do you get, 180? So we got 2,500. Now we got to subtract the mean, which is 2,870, over 180. And what is your z-score? Negative 2.1, is that right? Can we go to 06 on our table? We can, can't we? Yeah, let's do that. If we can go to the hundreds, let's go to the hundreds. So negative 2.06. Whoa. So just by looking at z-scores, we're going from negative 0.41 to negative 2.06. Which one's got to have a lower probability? Yeah, this one has to be way lower, just by general purpose. Because if this is your mean, negative 0.41 is going to be there. Negative 2.06 is way out over here. So all you're finding is that little bit versus all of that from negative 0.41 over. So negative 2.06, negative 2.06 right here. Is that right? Negative 2.06. So in other words, 1.97%. But you really need to understand why. That's my biggest concern here. Could I teach you how to type all this into a calculator? Yeah, but you're going to have no clue what you're doing.
So as the n increases,
Your standard yeah, your mean shoots way higher because there's more frequency towards that mean. Because all you're taking is a mean value. So this is saying you went out, let's say each of you did it. Each of you went out and got 25 of these card holders and you found their balance. And then you took the average. And the only information you gave me was the average. That's all you gave me. That's the central limit theorem. It's going to take, that standard deviation is going to shrink huge. And where's that information got to go? It's got to go up as far as that graph is concerned, right? And so your mean doesn't go anywhere. That's what all of this is saying. Your mean doesn't go anywhere. But everything squeezes towards that mean because you're all giving me means. All right? And so I would expect it. The reason that is look at this standard deviation. It's now only 180. We're going to try and get all the way out to 2,500. That's going to take a couple of standard deviations, isn't it, to get that far from 2,870. It takes a little while to get that far out. So I'm only finding that little bitty area because we are squeezing this thing in. Okay? So really what it means is that if I pick an individual, so if I take an individual out of that whole population, I pick an individual, what % chance is that person going to have a balance that is, what, less than 2,500, right? I just go out there, all those people, and I pick one of them. Does that have a pretty good chance? Yeah, all these people, not just the 25, all of them that they took this information from. And I just go ask one person. There is a good chance they're going to be below that because what's the standard deviation in that case? It's 900. So there's a pretty good, what was it, 34.1% chance if I look at just one person. But now if I start looking at a sample of 25, wow, there we go, of 25, well, I'm not going to look at just one person. I'm going to look at the what? I'm going to look at the mean. Okay. So if I take a sample of 25, there's only, what, about a 2% chance? We'll say, what is it, 1.9, so we'll say 2% chance that the mean balance is less than 2,500. Is it very possible that this individual is in that sample of 25? It is, but there's also other people in that sample of 25. Some of them that probably have a $3,000 or a $4,000 balance. And so what do is they bring everything towards that mean. So the chance that whole group ends up having a mean that's less than 2,500 is very slim. Yes, that individual could be in there, but again, there's other individuals in there. Do you get it? Kinda? Okay. The reason that standard deviation keeps shrinking in is of course your values are going to get closer to the mean. So your variance is going to be less if all you're looking at is the mean. Your variance has to get less, which means your standard deviation has to get less. So if you get this one, I think you're okay. And really, if you get the fact that it's very possible to start off like this with your distribution and keep squeezing it in. I know, I love it over here. You don't have to worry about markers or anything. And what's really changing from black to red to green to blue? Yes, the standard deviation's changing, but what's causing it to change? The n, exactly. So in that, what, numbers 11 and 12 for today? N was 100 on that thing. It's going to take this and just smush it huge. Like I say, where's that data got to go? It's got to go up this graph. It squeezes everything to the mean. Okay? Any questions? So I think what we'll do is tomorrow we will actually do the assignment on this. If you want to get started, it is pretty much the rest of the packet. You can start on it if you want. You don't have to. But we are not going to do, so if those of you that are going to work ahead a little bit, we're not going to do 18 and 20. Okay? But we are going to end up doing the rest of that packet. But yeah, don't worry about those two. No, it won't necessarily be into. I mean, if we get done with it tomorrow in class, we'll correct it. But, yep.